So before we begin talking about go back N and selective repeat, let's take a look at one more thing regarding pipelining. And that is how pipelining can increase your utilization. So imagine here you have a sender and a receiver, and there's some distance, and therefore a timeline at the sender and at the receiver. So the sender sends a packet at time t equals 0 that is received at some later time, and of course it takes time for all the bits to arrive, so there's a time frame from when the first bit arrives to the last bit arrives, and then an acknowledgement can be sent. So imagine our sender is set up so it sends 3 messages, then waits for an acknowledgement. Basically, what will happen is you're able to send 3 messages in the round trip time, the time between when the last bit of the first message is sent till the time the acknowledgement arrives. If we only sent 1 packet at a time instead of 3, you would only have sent this 1 packet during that same round trip time. So basically, you've increased your utilization 3-fold by doing pipelining. So let's talk a little bit about the 2 different pipeline protocols, go back N and selective repeat. And as we go through, we can talk about the advantages and disadvantages of each one. So in go back N, the sender can have up to N unacknowledged packets in the pipeline. And on the receiver of go back N only sends a cumulative ACK. It doesn't send an acknowledgement if there is a gap in the number of packets, in the packets that have been received. This will be very important as we talk about this mechanism going forward. The sender has a timer for the oldest unacknowledged packet, and when the timer expires, it retransmits all unacknowledged packets. In selective repeat, as before, the sender can have up to N unacknowledged packets in the pipeline, just like go back N. But in this case, the receiver is going to send an individual ACK for each packet instead of a cumulative ACK. In this case, the sender is going to maintain a timer from each unacknowledged packet. When the timer expires, retransmits only that unacknowledged packet. So you can see the advantage of go back N is on the sender and receiver, and there's a little bit less processing. A little less on the receiver because it's not going to send a cumulative ACK. A little less on the sender because it only has 1 timer. The disadvantage is going to be on the selective repeat. The disadvantage is, for go back N, is when the timer expires, you're going to retransmit all unacknowledged packets. So you're going to send more data across the network. So you'll be less efficient in your network utilization, but you're going to do more work in your network processing, in your operating system, and your network card. So this has the opposite. You're going to do more processing, but you're going to be more efficient in what you send across the network, basically only retransmitting unacknowledged packets. But now you have the extra work of having a timer for each unacknowledged packet. Okay, so we went a little bit too far. So let's take a look at a little diagram of a go back N sender. In this case, we're going to have a k-bit size sequence number in the packet header, so we can keep track of the packets and make sure, be able to tell whether or not they've been received out of order. We're going to have a window of up to some number n, where this is going to be how many consecutive unacknowledged packets are allowed. So green represents already acknowledged packets. So every time you get a package acknowledged, If it's the lowest one in this window, we slide the window to the right. So these yellow ones have been sent but have not been acknowledged. And these blue ones are usable. In other words, they can be sent because the window size is not full yet. So what we're going to do is, if we reach this end without any acknowledged packets, we're not going to allow any more packets to be sent out. Now, when we ACKs can be acknowledged up to all packets, including sequence number n, and this is called a cumulative ACK. We'll see an example of this as we go forward. It'll make more sense. And we may receive duplicate acknowledgments. And we'll talk about why when we look at how the receiver works. There is a timer for just the oldest in-flight packet, and we have a timeout, and when that timeout value is hit, okay, if we don't reset our timer, we're going to retransmit packet n, okay, because that's basically a timeout for the oldest packet, and all the higher sequence number of packets that have been sent that are in the window. So, for example, this timer, when this packet timed out, we would resend all of the yellow packets. So, the go back end sender responds to 3 different types of events. The first event is when an application tries to send a packet through the socket to the transport layer. For those of you in the 475 class, remember this as the RDT send function. When that function is called, the sender checks to see if the window is not full. If it's not full, then a packet can be created and sent. If it's full, then the sender tells the app that the window is full, or some sort of semaphore is used to allow the app to only send when the window is not full. Another type of event is the receipt of an acknowledgement. An acknowledgement for a packet with a sequence number n is taken to be a cumulative acknowledgement, indicating all packets with sequence number n have been up to sequence number n have been correctly received at the receiver. Finally, there is a timeout event. So there's some value that's set that if the oldest packet has not been acknowledged, sorry about that. If the oldest package has not been acknowledged, the timer will be set. So basically, the timer is used to recover from lost data or acknowledgement packets, because sometimes the data can be lost, sometimes the acknowledgement can be lost. If a timeout occurs, the sender resends all packets that have been previously sent but not acknowledged, so all those packets within that window. The timer is a timer for the oldest transmitted but not yet acknowledged packet. If an acknowledge is received, but there are still additional transmitted but not yet acknowledged packets, the timer gets restarted. So what's basically going to happen if an acknowledgement is received, the window is going to slide to the right, and the next new packet is going to be the oldest packet not acknowledged, and the timer now is applied to that packet. If there are no outstanding unacknowledged packets, so once all the packets have been acknowledged, then the timer can be stopped. Let's take a look at go back and in action. So in this particular graphic example, we have a sender window, so we're going to send up to 9 packets from sequence numbers 0 through 8, and we have a sender window of size 4. So that means the sender is going to send 4 packets, in this case 0 through 3. Then it's going to wait for acknowledgments. So here's what happens. Here we have the sender and its timeline, and the receiver and its timeline. And obviously there is some time it takes to go from the sender to the receiver and vice versa. So the sender starts off with the sender window going from 0 to 3. So it sends off packet 0 through 3, and then it waits. In this case, packet 0 is sent to the receiver. It acknowledges. Packet 1 is sent. It acknowledges. Packet 2 is sent, but it's lost. So now the receiver receives packet 3. So if the receiver receives a packet out of order, it does not it does not give it to the application. It basically discards it and will resend the last good acknowledgement. So eventually the acknowledgement from packet 0 is received. This allows us to move our sender window to the right by 1 and allows us to send packet 4, which we do. The receiver receives it, but discards it, and then resends the acknowledgement for 1. Then, at this time, the acknowledgement for packet 1 is finally received. The sender moves the sender window by 1, so now it can send packet 5. It sends packet 5. Now, the sender receives a duplicate acknowledgement for packet 1, but it basically drops it on the floor. It doesn't do anything with it. And now what happens next is now the timeout value for packet 2 has expired. Never received the acknowledgement because the receiver never received it. So now the sender resends all of the packets starting with packet 2 that have been sent but not acknowledged. So we haven't sent anything beyond packet 5, so we're going to resend packets 2 through 5. Now that the receiver finally receives a packet 2, it's able to deliver it to the application and send an acknowledgement, and then so on and so forth. Next, let's take a look at selective repeat. Okay, in selective repeat, the receiver individually acknowledges all correctly received packets, and it will buffer packets as needed for eventual in-order delivery to the upper layers. This is different from go back N, where go back N will stop acknowledging packets if the packets are out of order. In selective repeat, the sender only resends packets for which acknowledgments have not been received. And instead of having a timer just on the oldest packet, unacknowledged packet in the window, it sets a timer up for each unacknowledged packet. So the sender window will have n consecutive sequence numbers, and this limits the number of sequence numbers sent and the number of unacknowledged packets. So this is what the selective repeat sender and receiver windows look like. So basically, on the sender side, you have your sliding window of size n, and you start here, and we're going to call this first one, we'll call that send base. Okay, that's the base value for our sequence number. And right now we've sent all these packets, the green and the yellow, and next sequence number is set to the next packet that we're going to send. So yellow means that we sent it but not yet acknowledged. Green means already acknowledged. And blue means they're usable because they're within our window, but they haven't been sent yet. On the receiver end, we have packets, some of which are received out of order, so we've buffered them, but we've already acknowledged them. We have some, because we believe we're going to receive all the packets that we are expecting, but we have not yet received. And receive base is the starting point of our window. And we, at this current time, expect to receive packets within these values because we are maintaining the same window size. So let's take a look at what's happening with the sender and with the receiver. So in selective repeat, the sender interacts obviously with the application above it. So it receives data from the application. If the next available sequence number is within the window, the packet can be sent. There's a timeout value for each packet, value n. If the timeout value is reached, we're going to resend packet n, and then restart the timer. If the acknowledgement is within the set of from send based to send base plus n, so send base, okay, it's going back here. Send base is the sequence number of the first packet in the window, and send base plus n, okay, so n is the window size, so send base plus n would be right here. If we get that acknowledgement that's within this range, we mark it as received, and if n is the smallest unacknowledged packet, then we can advance the window base to the next unacknowledged sequence number. So if we received the acknowledgement for this packet, we could then move this window down by 1 to this packet. Okay. So if the packet n is in between receive base to receive base plus n minus 1, which is in this window here, this is receive base, and this is receive base n minus 1. We're going to send an acknowledgement. If it's out of order, we're going to buffer it because we're going to assume we're going to get the other packets. If it's in order, we're going to deliver it to the application, and we're also going to deliver the buffered in order packets, and then advance the window to the next not yet received packet. So kind of going back to a graphical example. So let's say this becomes this packet here is received. These two are already received, they're buffered. Based on what we said, we would basically move the window over to here. If the packet is in receive base minus n to receive base minus 1, which is basically the previous window. Basically, if this is happening, that means we basically, for some reason, the sender is resending an old packet. We've already taken care of. We're just going to send. We're going to send an acknowledgement. If it's anything else, which would basically be on the other side of the window, which would be, the sequence number is, corrupted or something, we're going to ignore that. So let's walk through this timeline and discuss how selective repeat works. So it looks a little bit similar to the go back and setup. We still have our sender window, and we're still going to send of size n equals 4. We still send 4 packets. And still as before, packet 2 gets lost. So packet 0 gets sent, and acknowledgement is sent. Packet 1 gets sent, and acknowledgement is sent. Packet 2 gets lost. Packet 3 gets sent. Okay? We don't resend acknowledgement 1 like in the past. We send acknowledgement 3. And we buffer packet 3 because we know we have a packet that's missing. Packet 0 is acknowledged, so I can move my sender window over by 1. And this puts 4 in the window, so I can send packet 4 to the receiver. It's going to buffer it. We receive our acknowledgement from packet 1. So now I can slide the window past 1 down to my next one, allowing me to send packet 5. I send packet 5. I get an acknowledgement from packet 3. But packet 3 isn't the oldest packet in the window, so I don't move my window. So there's nothing I can really do. And then enough time has gone by that the timer for packet 2 is set. And the timeout value has been reached. So now I send packet 2. Now the receiver can deliver packet 2 as well as packet 3, 4, and 5. And now it can send the acknowledgement. So now what's going to happen when the acknowledgement for 2 arrives? Well, what's going to happen is it can move over, the window can slide over, it can slide past 2 because 2 has been acknowledged, and it can slide past 3 because 3 has been acknowledged, and now I can send packets 6 and 7 because they'll now be within the window. Now let's take a look at a little bit of a dilemma. And this is basically caused by a little problem between the sequence number size and the window size. So, in this example, we have sequence numbers 0 through 4. So we change sequence numbers after 4, then we go back to 0, and a window size of 3. And we have 2 different scenarios, one in which the first scenario, packets 1 through 2 are sent successfully, and packet 3 is lost. And the other one, packets 1 through 2 is sent successfully, the acknowledgements are lost, and then packet 0 is retransmitted. So let's see what happens in these 2 scenarios. So in our first scenario, we start off with our sliding window going from 0 through 2. So packet 0, 1, and 2 are sent. So the receiver receives 0, slides this window to the right, and acknowledges 0. It receives 1 and slides this window to the right and acknowledges 1. It receives 2, slides this window to the right, and acknowledges 2. Packet 3 is sent, but not received. Well, is sent, but it gets lost. And then packet 0 is sent. The receiver will receive packet 0 and will accept that packet because it's within its window. So there's actually no problem here so far. Nothing has gone wrong. Now in this case, packet 0, the window is here, so packet 0, 1, and 2 are sent, and the receiver receives 0, 1, and 2 and moves its window accordingly. The problem is, for some strange reason, the 3 acknowledgments all get lost. So, which is kind of odd, and probably not a good real-world example, because if you can send all 3, the chance of all 3 getting lost in order is, that's not what usually happens. But in case that did happen, now, this time, the sender is going to send packet 0, but it's the original packet 0 because it hasn't moved its window. The receiver will think it's this packet 0 within its window. And this basically illustrates a problem where if our sequence numbers have to be, significantly, well, at least somewhat larger than our window size, so we don't have this type of confusion. That's the end of this part of our lecture, and now we'll move on to the next narrated lecture for today's learning module.